All right, we've got one last example here, and it's got kind of a lot of elements to it. A fireworks shell is accelerated from rest to a velocity of 65 meters per second over a distance of 0.25 meters. How long did the acceleration last? Calculate that acceleration. So we've got a fireworks shell being launched. That's our situation. Let's sketch that here. So we have our firework. We have it being launched, so going to some position later. Yes, a firework can normally be launched up, but it's totally fine to do it sideways because we just care about the one directional motion at the time, for the time. So delta x equals 0.25 meters. We know that the final velocity is equal to 65 meters per second. And because it started at rest, we know the initial velocity is 0 meters per second. We're asked to find what is the time, and we're asked to find what is the acceleration. So we'll label those on there. And now we've got our sketch. Let's write out some equations. So I know I've got an initial velocity, a final velocity, and a delta x. So I could either solve for a first or for delta t first. I know that just from experience and looking at this with the eye of a teacher, I know technically solving for the delta t is going to be a little bit simpler and easier to work with. So let's do the a just so you see the harder thing and see that if you did it differently, you'd still be okay. So, and by harder, I just mean the math is a little bit messier. To do it this way. But with v, delta x, and a, I know the equation I want is v squared equals v naught squared plus 2a delta x. So now we want to isolate the a here. So I'm going to do v squared minus v naught squared equals 2a delta x. And we're going to get that v squared minus v naught squared over 2 delta x equals a. That's just algebraic rearrangement. A is now isolated, so I can plug things in. 65 meters per second squared minus 0 meters per second squared over 2 times 0.25 meters equals a. So 65 squared, I don't know what that is, and I don't have a calculator right near me, but it's going to be 3,600-ish. So about 3,600 divided by 0.5, so double that, we're going to get something in the neighborhood of, I'm guessing, about 8,000. And now let's check our units. We have meters squared per second squared on top. And then we're dividing by one set of meters, so that cancels the meters. And so by my estimate, I'm getting an acceleration of about 8,000 meters per second squared. If you want to double check that and run that and let me know, but it should be in that ballpark. Let's check to see if that makes sense. 8,000, that's really big, but also we're accelerating, so, and it's like launching a firework. I wouldn't necessarily think that that's terribly absurd. It is in that like yellow flag territory. So if I actually had a calculator and this is what I had gotten, I would go back and recalculate it, but I wouldn't be insistent that I did it wrong. The units are correct, though. We have meters per second squared. That is for an acceleration. And the direction is correct. It should be to the right. It should be positive. That looks great. Let's jump back over here and deal with velocities and times. And so the equation that relates velocities and time is that the average velocity equals the change in position over the change in time. But remember that the average velocity is also equal to v plus v naught over 2. So let's isolate this for delta t. We're going to get delta t equals delta x times 2 over v plus v naught. That's just algebraically rearranging for the delta t here. Let me just double check, make sure that looks good. Yeah, I think so. So then delta t equals 2 times 0.25 over 65 meters per second plus 0 meters per second. Meters go in there. And we'll get 0.5 over 60, which means we get approximately 1 over, actually we'll get exactly 1 over 130. And then our units are meters times seconds over meters, because if we want to bring these denominator units up top, we need to invert them. The meters will cancel. So we get delta t equals 1/130th of a second. Let's check that. Seconds, great amount. 1/130th, that's a small amount, but also fireworks are launched real fast, so I feel like that's reasonable. And it is a positive time. That means that the firework was traveling faster later. That sounds good. Now, when I had said that it would be easier or quicker to do delta t first, that was because I knew if you got to this, then you can use the velocity, the change in velocity. You could use this equation here of delta v equals a delta t with the delta t you just solved for to find a. Which we can actually just double check to see our estimate is. So basically it should have been 65 times 130, which would be 6,500 plus another 1,800. So yeah, around 7,000 something, 8,000 something. I think we're a little high, but it should be in that ballpark. So now you're gonna want to jump into some practice problems, and I'll be available to help you out.